from University of Barcelona in Catalunya, Spain, and she will speak about a class of stochastic PDEs driven by fractional noise.
Yeah, thank you very much. So perhaps today I will disappoint some of you because actually it will be a very few probability in this talk. But the reason why I have chosen to talk about this is because at the beginning of the semester and also at the beginning of my visit here in April, there have been several talks on pathwise approaches to stochastic differential equations and to stochastic partial differential equations, and also some work by Maslowski and Wallard was mentioned. And I would like to maybe to complete a little bit the picture in this direction of pathwise calculus, although it's a topic that I am not more working on. So what I will talk today is based on joint work with Pierre Guillermo, who has appeared last year, and this is the plan of the lecture. So first I will here. Yeah. So first I will give a description of the SPD I am dealing with. Then I will introduce the stochastic integration suitable to deal with this SPD. We will introduce two types, actually classical types of solutions, so variational and mild solutions, and we'll give the relationship between them. And then I will address the problem of the regularity of the sample paths. And finally, I will discuss on uniqueness. You will see that uniqueness is a delicate matter here. Okay, so the SPD is SPD, which is, except for this term, is a very classical one in analysis. I have also written this in the board because, well, you should keep in mind the model throughout the talk. So the differential operator is here, okay, and it's a non-autonomous equation, because here the coefficient depends on space and on time, okay. So the initial condition is given by some function phi. This is an equation on a bounded domain with a regular boundary. So this is the precise description of the boundary. And well, I consider Neumann boundary conditions. So this stands for the conormal derivative with respect to the matrix valued field K. Okay. So of course, well, it's very classical, and so the extra term which is here is the stochastic term. So these are the free terms G and H. I will give the assumptions in the next slide. And so here the perturbation is fractional, an infinite dimensional fractional Brownian motion. I will also give the definition of that. So, and of course you see that this is a generalization of stochastic heat equations. So I am not aiming to be complete here about the references, of course, but well, just to mention a few names, the stochastic heat equation, of course, is included here and has good motivations, like problems in neurosciences, for example, and also such a equation, a little bit a simple model, have been already introduced by Dawson and Dawson-Gorostiza in relation with problems of evolution of populations, and further studied by many people. So I mentioned Krylov as an example. So the assumptions on this equation are, so concerning the free terms G and H, there are Lipschitz functions, and then concerning K, so the function here in the operator, we are assuming that it's symmetric. So for any x and t, it's a symmetric matrix and is strictly elliptic. So here you have the definition. And this implies that this operator is self-adjoint and positive, and this is something which, of course, when dealing with this equation, is very important. And I also have written here that K is regular jointly in X and T. So I didn't formulate precisely the assumptions, but regularity means that some Hilbert continuity both in X and in T, and also some Hilbert continuity of the partial derivatives with respect to X. Concerning the initial condition phi, I am assuming that it's of class C2 plus vita. Vita is the regularity of the boundary. And okay, so these assumptions are just to ensure that in the case where H is 0, so you have the deterministic problem, this equation has a solution, and well, it's very well known, the properties of the solution, and I have given here a classical reference also. The second reference, which is also very complete, is Vladisemskaya, Solonikov, and Uralsheva. Okay. Sorry. So now, what about the noise? The noise I am considering is an infinite dimensional fractional Brownian motion. So take this definition as the noise, and I will now explain what it is about. So here I am considering infinite sequence of independent fractional Brownian motions. Okay, so that means that by means of this series, what we have is a noise which is fractional in time, but in space it is colored. And the color is given by these coefficients, lambda, so to be more precise, so this is a cylindrical fractional Brownian motion. So as it is usual, you consider a self-adjoint positive non-degenerate trace class operator, C, on L2. And then you consider bases, orthonormal bases, consisting of eigenvectors of these operators. So these are the EI. Always you can assume this property here. And then you consider the corresponding eigenvalues. And since the operator is trace class, the series of the lambda i's is convergent. And here I am assuming much more. So I am assuming square integrability. Okay, so sorry, square integrated. So the square, the summability of the squares of the eigenvalues. Okay, so this is the color we put on the noise, and this is the dependence on the space. Oh my God. Okay, so just for those who are not familiar with, I will just recall what is the usual one-dimensional fractional Brownian motion. So this is a Gaussian process whose covariance is given by this formula. So a Brownian motion depends on a parameter which is called the Hertz parameter, and such an object is already mentioned in some work by Paul Levy in the 20s, although most people refer to Mandelbrot and Van Ness for their popularization. So this is Brownian motion, and when h is equal to 1.5, you recover Brownian motion, and otherwise for h greater than 1/2 and h less than 1/2, you have so increments which are positively and negatively correlated respectively. Okay, so the sample paths of Brownian motion are nice. It's very easy to prove because it's a Gaussian process, and then you have the explicit form of the covariance that the increments behave like that, the L2 moments of the increments behave like that, and therefore since it is Gaussian, you get the Hilbert continuity via Kolmogorov's criterion, and the Hilderianity is of degree A less than H. So although trajectories are quite nice, the fact that the process has not independent increments, and it's also known that it's not a semi-martingale, we cannot apply Ito calculus, and this is the source of problems, but also of interest of this process. So before going on, let me give some references to give a precise frame of our work. So these are the more fundamental, of course. So in this reference here, so first let me tell about the infinite dimensional Brownian motion. Okay, so the case where h is equal to 1/2, so cylindrical. In this paper, in this joint paper with Pierre, we have studied this equation, exactly what I will tell you today, but for the case of Brownian motion, and of course the techniques are completely different because here we can use Ito calculus. Okay, more general operators and also more general free terms G and H, but one-dimensional, because here we are dealing in dimension D in general. Okay. And with finite dimensional Brownian motion, so there is work by Laurent Denis and Stoica, and also Laurent Denis himself and other collaborators, but here is just a sample of one paper, one single paper, where they prove existence and uniqueness. And then very recently, so this year, there is this paper by Ferrar, who was visiting also the semester, where he actually extended our results for a type of equations more general than ours on Banach spaces of this class. Okay, and in fact, the example that he develops, where his theory applies, is actually our example, and it's nice because he's able to improve our results on Hilderianity. So then, concerning fractional Brownian motion, there is one paper who was mentioned here in I think that by Sami Tindall or by Maslowski and Noalard, where they are dealing with fractional Brownian motion, so the same type as ours, for Hertz parameter greater than 1/2, but the operator driving the equation is autonomous, so it's not so general. And finally, also Noalard and Villermo studied this equation, exactly the same equation, but so this is actually the starting point of our work, because they prove existence of solution of variational type, so only the existence. So our work is a natural continuation of that one and that one, in the sense that we complete the program we carry out on the Brownian motion, but that time for the fractional Brownian motion. Okay, so what sort of calculus one can use? So let me give a brief overview, because maybe not everybody is familiar with. When one wishes to deal with fractional Brownian motion, in my opinion, there are two possible approaches. So one approach is what is called the pathwise approach, and another approach, which is really probabilistic, is using Malevin calculus. So concerning the pathwise approach, there are mainly two lines, or two ways. One is using fractional calculus, and the other one is using Roth-Path analysis. Okay, it's not, well, of course they are comparable and they are linked, but it's not the same. So here I put also a few names, not all of them, of course, and I would like to stress the fact that fractional calculus is very much suitable to deal with fractional Brownian motion in the case where h is greater than 1/2, but not only, but mainly in this case. Though Roth-Path analysis is suitable to deal with this process when h is greater than 1/4. We cannot go below that. And so then, using either one or the other approach, there are applications either to stochastic differential equations. Here also I put some names I didn't repeat, so Roth-Path family means all these people and many more. And then also some cases of stochastic partial differential equations. I would say that applications of Roth-Path analysis to stochastic partial differential equations are at a very preliminary stage. We have listened here some talks, but well, the truth, rough path analysis applied to equations, well, at the moment, they only cover a very restricted class of equations. So, but of course, it's a promising topic. Then the approach using Malyaven calculus has been initiated by a very nice paper by these three authors in 2001, where actually they developed Malyaven calculus with respect to Gaussian processes. And the idea here is that, well, using this Malyaven calculus, one can develop stochastic calculus with respect to fractional Brownian motion using representation of fractional Brownian motion with respect to the usual Brownian motion in terms of a kernel. So you see like Volterra integrals appear. So what is so this is a nice approach in the sense that well, I found it nice because it's very much probabilistic. But on the other hand, what happens is that when you are inside this framework, you immediately face the disadvantages of anticipating calculus. So why I say disadvantages? So this is because it's complex. So calculus is nice, but in practice, to apply the formulas, so this is really heavy, and so. And this is why I have written here that applications not extensively developed. So because of the complexity. Of course, this is a pity because, as Sami Tindall mentioned in his lecture, there are in the literature in very different topics, in engineering, biophysics, mathematical finance, you find models where they use fractional Brownian motion, and they have stochastic differential equations and SPDEs, and not always h, well, makes sense to assume that h is greater than 1/2. Okay? So here we are going to use the approach based on fractional calculus. So don't be scared about these formulas. It's just you know to fix definitions. Okay. So to introduce the integral I am dealing with, we need to know about the definition of Riemann-Liouville integrals and their derivatives, which are normally called Marchot derivatives. So it depends on the authors of the books, if they are German or they are French or they are okay. So let's fix this notation. So Riemann-Liouville integrals appear in solving what is called the Abel equation. So this is a very nice equation. There is full theory behind that. I will not speak on that. And they are defined in that way. So this is a very not very difficult. Gamma stands for the gamma Euler function. Okay. And then once you have the Riemann-Liouville integral, so this is called the left and this is called the right Riemann-Liouville integral, then you can define a sort of inverse operator. Okay, and these are the derivatives. So these derivatives with this formula, so this is on the left, on the right, are well defined for functions f, for example, in that case, for the left derivative, for functions which are integrals of this type of functions of LP, okay? And the same or similar for that ones. So we have these definitions, and with these definitions we can really develop a calculus. And then the idea of Marta Sanz-Solé in a seminal paper in PTRF in '98 was the following. So let's give an extension of Young's integral, of what I call a generalized Stieltjes integral, in order that we can use the fractional Brownian motion as integrator. Okay? And so here is the definition she gave. So you fix parameters P and Q related in that way, and then alpha related with P in that way. And let's take F in this space, and G, or so roughly speaking, G in this space. Okay? And then we can define the integral on a fixed domain A and B of Fg by this formula. Okay? So then, of course, the problem is what sort of f and j's are examples of integrants and integrators, well, to describe these functions in such a way that I have not to compute the derivatives. Okay? And this is a short explanation. So let's introduce norms. So a norm, which I will call alpha 1 norm, which will be suitable for the integrand, and for the same value of alpha, I introduce a norm which will be suitable for the integrator. Okay, so these are sort of fractional Sobolev norms. And then what Marta Sanz-Solé proved, and also in this exactly form in a paper by Rascanu and Noilard, is that in the case where f has a finite norm, alpha 1 finite norm, and g 1 minus alpha infinity t finite norm, then the integral, the Sanz-Solé integral, is well defined, and moreover one has this inequality. Okay? So in fact here you can also deal with functions which take values on a Banach space. Or here I will deal with Hilbert value functions, and then just you replace the absolute values by the norms, and everything goes through. So you have also this inequality understood in the appropriate sense. Okay?
Could you please switch back to the definition of the integral, just one slide? Okay.
So then, you know, making computations
in the
on
inverse space, you should make
yeah.
this like weekly
Yeah.
in G and
Well, you work on coordinates, if you wish.
Yes.
It's not a big issue. Okay?
So
Sorry.
if, for instance, f and g they are in they are in this space E alpha for two difference alpha, the definition is consistent. And
Yeah,
it doesn't
yeah,
depend
yeah,
on
yeah, yeah.
Because, okay.
Yeah, exactly. Yeah.
Okay.
Okay. Well, I wanted not to go into the details of the calculus, but yeah. You are
What
right.
is h with respect to alpha?
Sorry?
How is h related to alpha?
What age?
The
Ah,
parameter.
you, yeah. Well, this will come very soon. It is. So now what we want is to see if fractional Brownian motion can be an integrator, and so what happens is that one has this property exactly. So if the Hurst parameters is greater than 1/2 and you take alpha in this range, then it is not difficult to prove that this norm has a finite first order moment. So this is really not difficult, because you see you can for a Gaussian process you can get estimates of the expectation of that and so on. So it's really not difficult. Okay. So therefore, from this condition, what you get is that this norm of the fractional Brownian motion is finite almost surely, and therefore now you can deal pathwise, right? Okay, so now let's see what sort of conditions will assure the existence of an integral which will be suitable to give a meaning to the SPDE I am interested in. So let's consider a stochastic process with values in L2, okay? And let's consider the components, so the projections on the basis of the Hilbert space, L2 of V, okay? And let's assume that the alpha 1 norm of this process is uniformly bounded on I, okay? Almost surely. So then, because of the estimate of the integral I have told you about in the last slide, you have this inequality here. Okay, so this is finite almost surely. We are assuming that uniformly in I, this is also finite almost surely. We have assumed that the square root of lambda i's are finite, so this is finite. And this is what we need to give a meaning to a stochastic integral. So I will define the stochastic integral of such a process with respect to the infinite dimensional fractional Brownian motion. So by definition, this will be a stochastic process taking values on L2 of D also, which is given by this sum. And this sum actually converges in L2. And well, this is the natural definition if you remember that WH has this expansion. Okay? So then we have also this inequality. This is a random variable which is finite almost surely, and so that is it. Is that clear? Okay. So now let's go back to the equation, and I will fix now the space where the solutions of the equation will live. So for that, remember that we have a Hurst parameter greater than 1/2 alpha in this interval, and I will introduce a Banach space of consisting of measurable mappings with values on L2 defined on 0t, such that this norm is finite. So this is the basic space, and if you remember, so here is the norm also, because I will use it very often. So if you remember, or just let me remind you, the norm alpha 1. So in fact, the norm alpha 1 is upper bounded by the norm alpha 2. Okay, because so this singularity is integrable because alpha is less than 1/2, and then by using a Schwarz inequality you go from here to here when you square. Okay, so okay, so this is the space, and now I will introduce two notions of solutions. So one is the notion of variational solution, which has been introduced by Noaillat and Wheeler-Moy in the last article, and this is a stochastic process, which I will call UV, which belongs to this space, intersection with the L2 space, the L2 of 0t, taking values on the Sobolev space H1d, consisting of functions which are in L2 and with derivative square integral. Okay, and then we assume, so there is a definition of variational solution, that for every test function in this space, so it's the same definition but now for functions which depends on the space and on time, you have the validity of this formula. So this is completely classical. You take the equation, you multiply by the test function uv, okay, you integrate over d, and then so this term here and this term here appears by integration by parts of the contribution of the divergence. Okay, so this is the classical. So we are going to introduce another also classical type of solution, which wasn't considered in the article by Noaillat and Wheeler-Moy, which is the Miles solution. So by a Miles solution, I understand a stochastic process living in the same space as the variational solution that now satisfies this equality here, where the G stands by for the green function associated with the operator driving the equation, which is this operator here, with Neumann boundary conditions. So let me recall also some very classical fact, but which is crucial in all the computations we should perform, and is what I call the Gaussian property. That means the behavior of the green function associated to this operator. So a green function, now there is a non-autonomous problem, so it depends on these four arguments, there is no stationarity, and this function is twice differentiable in space, one differentiable in time, and these derivatives, partial derivatives, behave like the heat kernel. Okay, so they are upper bounded by this expression here, where mu is a multi-index and nu is just an index, and the restriction is that one. So twice in time at most, twice in space at most, and one in time at most. Okay? So this is also very classical, but very important. Okay? So why we have introduced this space B alpha 2, or what is the role which this space plays? So in fact, when we have set up the definition of a Miles solution, one may wonder if all these terms actually, if we are looking for a solution which is in that space, if all these terms make sense in that space. Okay. So just to see why this space appears, let me be a little bit technical. So consider, for example, the stochastic integral term, which is of this type. Okay, this was the stochastic integral term in the Miles solution. So to simplify the notation, I call the integrand, which is this red part here, fit. Okay, and if you remember, in order to give a meaning to this stochastic this pathwise integrals, sorry, you have to get nice estimates for that. Okay, and so the estimates were in terms of the norm alpha 1, you remember, and the norm alpha 1 is just that. Okay, so now for this term here, you see that here you have the definition. You want an upper bound for the L2 norm. So in fact here what we are going to use is the fact that G is integrable. Okay, so this is like a heat kernel, and H is Lipschitz, and therefore it has a linear growth, at most linear growth. Okay, and then when you study these terms, since this is not singular, it's integrable around 0. So then from here, from this term, you get just the norm of U. Okay, but in order to study the second one, so here things are a little bit more involved, because here you have an increment of f at different times. T and S, okay, and so here you have the definition. So that means that you have to deal with increments of G and increments of H, okay, and it's precisely you have these two terms here, okay, increments in H, which by Lipschitz property gives that, and increments of G. Okay, so then when analyzing this term, we'll have this second part of the norm. Okay, and here, when you analyze this term, you have to use the nice properties of G. Okay, and keep track of the differentiability and basically of the differentiability in time. Okay, so that means that here you obtain some power of t minus sigma, which in fact kills you kills or makes better this singularity here. And so that this term goes together with that. Okay, so this is the way by which this norm appears, or in a natural way. Okay, so now let me describe the results. So here are again the assumptions, not very detailed. So I am assuming something which I have not said yet. And it's that H is differentiable and the derivative is gamma Hilbert continuous for some value of gamma. And the theorem or the results we have on the equations are as follows. So we fix a Hertz parameter in an interval which depends on this Hilbert degree. Okay, and then alpha accordingly. So first there is the result by Noir and Villermoz, who says that the equation possesses a solution in the variational set. This was their result. And then as a second result, we have that every Miles solution every variational solution is also a Miles solution. And more precisely, what we have is that for fixed t, both functions as L2D valued functions, as functions of L to D coincide almost surely for any t. So this is second result. So then third result is uniqueness. So uniqueness, unfortunately, the problem is not completely solved, and I will try to explain why. So it needs H to be affine. So this is of course very restrictive, and moreover we are only able to state uniqueness in under more restrictive hypotheses than existence. So remember that in the previous slide H was supposed to belong to the interval 1 over gamma plus 1, 1, and here is a little bit more restrictive. Well, more restrictive, and the restriction depends on the dimension. This is the dimension of X. Okay? So we have this result about uniqueness, and then the last result is the sample path properties of the Miles solution. Here we have this estimate, which tells you that in T the solution is Hilbert continuous, and with degree zeta, which belongs to this interval. Okay, so this is what we know about this equation. So then, of course, in the case where H is affine, we have indistinguishability of both type of solutions, variational and mild. And then, of course, we may wonder what is the role of the nonlinearity H, or what happens in the case of additive noise. So in the case of additive noise, things are much more. So you don't need fractional calculus and anything, because then you can really from the beginning work pathwise. Okay, and so going through the proofs and simplifying many things where really the fractional calculus is not necessary. It's very easy to prove that one can have existence in this space, which is of course much. So it's a stronger result, and also we can have Hilderianity of this order, and in fact this order here comes from the initial condition, from the contribution of the initial condition. So, but I mean, this is really like a toy model, and very easy case to deal with. So here all the difficulties come from the nonlinearity of H, I would say. Okay, so now about the proof. So first, as I mentioned, the existence of a variational solution has already been proved, and just to let you know that it's a variational method based on Galerkin scheme. This is really, so this is a very long paper. It's very technical. So this is not easy at all to achieve. And then, in order to prove that also there exists a Miles solution, we go the approach is the following. We prove that every variational solution is a Miles solution. Okay, and this actually simplifies, I think, the approach. Because, well, in order to prove that such a Miles solution exists, one is faced to fixed point arguments, which in fact here they are difficult to consider because of the norm of the stochastic integral. So this is the main problem. So fixed point arguments for general H are not, well, I think that one cannot use this sort of arguments, okay? But in the case where H is affine, we can use a sort of fixed point argument. And this is actually what we use in the proof of, well, this is the proof of uniqueness. And then, well, Hilderianity, we'll see some slides. So it's established using accurate estimates on the increments of the green function, and one could also approach the problem of Hilderianity using what is called the factorization method. If I have time, I will show some slides on that. But what happens is that, well, with this approach, Hilderianity is obtained much easier, but the results are worse. So the degree of Hilderianity one can reach are worse. So I don't know why. I mean, it's really due to the method, which is quite surprising. So I don't have a convincing explanation. So, okay. So let me go through the steps of the proof, except for the existence of variational solution. So this is the approach is also quite classical. It's essentially technical. So we assume that we have a variational solution UV, okay, which is 2, and then we consider a test function, and the test function is defined by this expression here, where G is the Green function, remember, and we assume that V, so this is a sort of test function, is in C2 with compact support, okay? So then it's not difficult to prove that such a function belongs to the space of test functions we are considering, which is H1 of V across 0T, okay? And then what we prove is by using the properties of self-adjoiners of the operator and so on, that this expression here, which is actually, well, if we had here, well, v is equal to 0, would be the mild formulation of the equation, okay? So we are able to prove that all this function of space of x is orthogonal in L2 to every test function of this type, okay? So then, of course, since this is dense in L2, we get that actually this is equal to 0 for any v in L2, and therefore we get the equality of 0 as functions of L2, and therefore the mild solution. Okay, so this is the way it works. So now let me talk about the uniqueness. So in order to prove the uniqueness, and here we need h to be an affine function, let's consider this norm here, but I will now make it dependent on time, okay? So I just put here, so I consider the time between the interval 0t, and I change, well, maybe this is a bad idea, I would put t bar, okay? And now here t bar, okay? So just you restrict the interval to 0t for t in 0 capital T. And then what we are going to prove is that if you have two mild solutions, the difference of these two mild solutions, so this stochastic process, satisfies this inequality. Okay, and then you are done, because you can use a Gromwald's lemma, and you get the uniqueness. Okay, but this is not at all easy to establish. So how we can establish such an inequality? So of course, well, the natural way, there are not many choices. So remember that this norm has two components. So let's start first by upper bounding this term, where now the u is replaced by a difference of mild solutions. Okay, and then use that there are mild solutions. So you have an equation for u m and for u tilde n. Okay, and so upper bounding the L2 norm. Of course, you have to upper bound, so the term coming from the stochastic integral, the term coming from the integral with respect to Lebesgue measure, and well, after computations, you end up with something which is of this type. Okay, so this is nice because you see this part here is it's equal to the second component of the norm. So that means that in fact such an inequality gives you for free that the desired norm, which is that norm, can be also upper bounded by modifying the constants by that. Okay, but this is not what we wish, because what we wish is something as integral from 0 to t. This is okay, but this is not okay. Okay, because we want here to have this integral. So we have to work more and in order to include a further integral. So I must say, or I must stress, that this inequality is proof under the assumption that H is affine. Here, this really plays a role. And why we need this property? So the reason is the following. When you try to upper bound the L2 norm of the stochastic integral, you see an increment appear. Okay? So now, since you have the difference of two solutions, you will see appear two increments. So you have a sort of double increment. But you have the H, so it's a nonlinear. So without any property on H, it's difficult to get from this second order increment of HU something which will end up only with an increment of U's. Okay? So of course you may think, okay, but some degree of differentiability maybe will do the job. Of course we have tried such properties, but the problem is that you have also singularities, so you have to be very careful. So of course it's also a technical problem, but it's really a tough one. Well, we didn't manage to avoid this restriction, and actually in the case of the variational solution the same problem arises.
I'm sorry, could you say that again? You said you have also what? Did you say singularity?
Well, the problem is the following. Here you have the difference of two solutions, two mild solutions. Okay, so that means that you have to estimate two integrals with respect to the fractional Brownian motion, the difference of two of them. Okay, so then if you remember, when you estimate this integral, you have one term which is which is the L2 norm of U. So in that case, it will be the L2 norm of the difference of U's, which is okay. But then you also have increment in time of, so here it's an increment in time of H of U M. Okay? So now you have four terms, because you have an increment in time for UM and an increment in time for UM tilde. Okay? And you would like to deal with this term in terms so that at the end you obtain ZM minus ZM tilde L2 norm. And here is the problem. So well, if maybe we can discuss later, because you will see the details. Then, of course, if H is affine, the problem disappears. Well, disappears essentially. And then what I was saying is that, okay, you may think of adding some Hilder assumptions on H, as it is here the case, and then put together two and two of the increments and work separately. But this doesn't work. So. Okay. So now, as you have seen, we have to work further on this term here, okay? And now the idea is again, so we have an equation for Zn, and here we have an increment in time, right? So this term, you would like to see it replaced by this norm. If this can be replaced by that, then the inequality ready to use the Gromwall's lemma would be fine. So then maybe I will skip these technicalities because yeah, so this is really technical. So maybe just the idea is that well, when you develop further the previous this term here, so what happens is the following. So you end up with an expression like that. This is okay, so you keep it at it is, and the other ones are really quite involved. So you have terms which belongs to two different classes. Okay, one class is a term like that which only involves Zn. That means an increment of two, not an increment, but a difference of two Miles solutions. But because of the norm of the stochastic integral, you also have terms which involve increments in time. Okay, and of course, in the course of all these computations, you also have increments of the Green function, which you can estimate. Okay, so at the end, morally, you have some integrals where you have exactly terms of the type you wish and plenty of singular terms, which are factors. But what happens is that, there are enough integrations in order that these singularities disappear and you end up with a suitable norm. So this is, yeah.
In the work of Guillermo and Untitled, they have used the edge that is differentiable function, and by this they have used in fact 4 terms to be 2 and 2. You can do the same way?
No. In the work of Guillermo and Noalard for the uniqueness, they also use that H is affine. They don't know. I mean, it's the same problem.
Yeah. But they proved all the uniqueness for H affine function.
Yeah, uniqueness.
For the existence, we used
Yeah.
assume that H is a
Held
differentiable
there.
function.
No, Hilder.
Hilder.
Yes.
For
This
the
was.
functions and use it.
Yeah, this is why I put this hypothesis.
It's the same.
Yeah, it's the same
way?
hypothesis. No, because we prove the existence of Miles solution in an indirect way. So we prove that each variational solution, which was proved under the assumption that H is Hilder, is also a Miles solution. Okay? So for the existence of Miles solution, the hypothesis is that H prime is Hilder continuous. Okay? But even with this hypothesis, to prove uniqueness, either in the variational sense or in the Miles sense, doesn't work. This is. Okay, so then Hilder continuity, so the approach is quite direct. So you deal term by term, okay? So then here I only consider the stochastic integral, because in fact is the more complicated. This stands for the stochastic integral, so I have an increment in time of the stochastic integrals, which gives me 2 terms. One term, you see appear the increment st in the domain of integration, and in the other one, the increment takes place in the integrand. Okay, so this is fit, which is here, and the other term is integral from 0 to s to an increment of fyt in time, s and t. Okay, so for the first one, of course, you will get a power of t minus s, which is very good. So no worry about that. So more or less the arguments are those which I already told you. And then for the second one is also more involved, okay? Because we have to deal with some estimate of the L2 norm of this integral, okay? And then again you see the problem, but here is different because the increment is on the Green function. So you have again a double increment in time and therefore we'll see appear double integrands of the green function. And well, in order to get the right size of t minus s, you have just to apply here mean value theorem and use the properties of the green kernel in an appropriate way. So this is more or less the argument. So then, just to end the lecture, we could also use, as I said at the beginning, the factorization method. So this is a method which, for stochastic convolutions, have been set up in a paper by the Prato, Quapian, and Sapsi quite a lot of time ago. And factorization, so it is a good method to deal with a stochastic convolution. So here, or a stochastic convolution is this, okay? And factorization method consists in writing this integral, this stochastic integral, in another way. So you pass from a stochastic integral to integral with respect to Lebesgue measure. And you bounce stochasticity to the integrand. Okay, so this is essentially the method. So here y epsilon is defined that way. So this is the stochastic term, but now is an integrand. And the proof of this equality is very easy. So many people here are very familiar with that, and it uses the semigroup property of the green function of the semigroup, if you wish, and also Fubini's theorem, and also the definition of the beta function, which gives you this constant here. So, of course, you have, in some sense, make better things, because now this is a Lebesgue integral, but you have also introduced here some singularity. But, well, the smart thing is, what we should do is to choose epsilon in a nice way, so that you can control the singularities. Okay, so and then using this expression of the stochastic integral, you can of course try to upper bound the L2 norm of increments in time. Why not? And for that you use that in fact your integrand, which was the y epsilon, is nicely bounded. So this can be proved. Okay, so this is one thing to be proved. And then once you have that, you can compare the two stochastic integrals by dealing with these two terms. And this is much easier, because here now you don't have a stochastic integral. So you don't have you don't see this phenomena of appearing increments in time of the integrands. Okay, so in some sense it is easy. So you easily get, well, not very easily, but well, more easily that in using the other approach, that you also can upper bound the increments by some power of t minus s. But the degree we obtain is in most cases worse. Okay, so just to end the lecture, we can think of some further directions. As I told you, I am not more interested in this problem, but anyway, so maybe somebody could be interested in. So of course the main problem is what happens with when H is not affine. Okay. And then, well, I have some ideas, but I need time. And in fact, the idea is to use, so to say, fractional differentiation to deal with these increments in H. So be less rough that just use Hilderianity or things like that. And this is not, I mean, this is not just a fancy idea, because in fact, in a problem that has nothing to do with that one, and it was this memoir with Robert Dallang, where we proved the joint Hilder continuity of the solution of the stochastic wave equation in dimension 3. We encounter a problem which somehow it is similar, And then there, using the semigroup property of the RIS kernels, we managed to get the result, which is sharp. And so the decompositions of the kernel we use there, I think that maybe could work here, but this needs time and energy. So. And then another thing that could be very interesting, and we had been discussing with Laurent Denis, actually, is to try to extend these results for free terms which are more general. Okay, so it's a little bit to combine what we have done and what they have done. So what they have done with their techniques, they only are able to cover finite dimensional standard Brownian motion. So from the noise side is quite restrictive, as far as I know. Maybe they get recently more stronger results. But when I was discussing with him, this was the state with Laurent Denis. Do you know him?
No.
It's a brilliant French guy.
I'm sorry.
Yeah, Laurent Denis. He's in,
knowledge.
yeah. Yeah, he has very nice,
Unless you
very nice
maybe
work
you
with
write
the
the name
Stoica.
everywhere.
Yeah, yeah. But he's not traveling a lot, so maybe this is the reason why you don't see him. Yeah. So this is something that also could be probably done, but well, this should be also a difficult question. Indeed. Okay, that is it. Thank you very much for your attention.
So, other questions and comments?
Yeah, what if you try to take a Riemann approximation to, in other words, take a sum to approximate this stochastic fractional integral? Will you end up with the same thing or something different?
I haven't. We haven't tried this approach. You mean?
So I mean,
So you mean by?
when you first define the integral,
Yeah.
yeah,
Yeah, Riemann, like a Riemann.
I mean, what if you take a difference approximation to the, just
No,
try to
I
define
think
it
that
in the usual way?
You mean the definition of the integral?
Yeah, is it?
Yeah, I think at least under this is what happens with rough paths also. So I suppose that under.
Yeah, but this is rough paths, so.
You mean the sum of Riemann?
No, he means the stochastic integral, the pairwise integral. So if f and g are regular enough, I am sure that you can deal with such a position. But I am also pretty sure that the assumptions that you need must be stronger than the ones with the fractional.
Okay, but I mean, the way I understood your formula is sort of an integration by parts.
Yeah, it's a
But
Young
then-
integral, actually. It's a Young integral.
There were no boundary terms.
There was one.
Well, okay. So in other words,
I think it's possible to do what you have suggested.
I think yes, but I am not sure about the assumptions, Yeah.
sometimes the fractional integral is the boundary. You have to go over the boundary. Just
Yeah,
like,
yeah. Yeah, but
just
this
like
is.
with Levy processes are fractional Laplacians, and you jump over the boundary. So I'm wondering if the boundary term is somehow something much larger than you expect.
Yeah, could be. But this would be more not for dealing with the equation, but just for the integral, because if I understood well your question.
Yeah. So the question is, what is the motivation for this integral?
The motivation for what? For the
For the
this-
definition.
the
for
definition
this
of-
definition. This is an extension of Young integral. Just that. It's a pathwise. Yeah, it's.
So
So you're
Yeah, I
saying
mean,
that-
for Young integral, you need the integrand and the integrator. If you read the whole paper by Young, you need Hilderianity of both with a degree which satisfies some regularity. So here, the conditions on the integrand and the integrator are different because they are assumed. Okay, so here this is the difference.
but are you sure they coincide in some cases?
Yeah, sure, yeah. They coincide yeah. So this is general, this is why I wrote an extension of, this is an extension. But it's a Young type.
Yeah, so there are more questions.
So, because in this work, you assume that G and H are both Lipschitz. If it's the only how local Lipschitz condition, do you have any result on this?
Yeah, well, I mean, we put this hypothesis for the sake of simplicity. If you consider something which is local, I don't really see a problem because the approach is pathwise. So no, I don't think that. Well, now there are explosions. Well, not so sure. Well, an extension which could be much more trivial is to put coefficients which depends on time. This is appropriate hypothesis too. This yes, because actually this paper from Ferrar, the coefficients depends on time. Yeah, but locally, I suppose that could be done. But I don't know if explosion was.
Yeah, like a polynomial.
Yeah. Well, this no, this is not sure at all.
So in the same spirit, or in the spirit of your last remark, when you wrote G of U, gradient U, etc. So if you just take a simple model, which would be Burger's equation, do you know anything about this?
No, I haven't seen. Well, as far as I know, I haven't seen a Burger's equation with fractional noise. I haven't seen. No.
So, yes.
I have a question related to this operation. Because of you mentioned the fractional Brownian motion can be represented as integral with respect to usual Brownian motion with some integral kernel.
Mm-hmm.
So can you reformulate your initial equation as an equation with respect to usual Brownian or Gaussian measure with independent increments with special integral kernel, and then translate all difficulties to the integration between the head semigroup and this integral kernel?
Yeah, I am sure that you can. Well, this is the eternal problem. Once you have an equation, differential equation, then you give a meaning as an integral problem, and then you choose the stochastic integral. So of course you can choose the.
No, I am speaking that this pathway approach can be considered relatively to the integration between the deterministic parts. One part is integral kernel,
Yeah.
and another part this is grid function. And then this is equation of motivation, because then you can consider your initial equation as an equation with some kind of homogeneous noise and so on. So it is more relatively to physics, is more relation to physics, to Burger equation, for example.
So if I understood well, what you mean is, okay, so let's take the representation of this fractional Brownian motion, then this is a Gaussian process, and then I integrate with respect to this Gaussian process, but in a pathwise approach. Then you go to the Rothbard family. Yeah.
Yeah,
I mean, in principle, this is an approach, but
yeah, I think it's probably.
and then you will be more in the Stratonovich setting.
And continue the discussions in the coffee room or tea room.
Yeah, no problem.
So let us thank the speaker again.